So I will be talking about the theoretical foundations of nonlinear optics here. Let's see how do we compare linear optics and nonlinear optics in a very basic way. So in linear optics, the optical properties of a material, basically the refractive index and the absorption coefficient, they are independent of the light intensity, and the principle of superposition is applicable. And the frequency of light, that's the color, is not altered by passage through the medium. And then two beams of light don't have any effect on each other when they pass through the same region in a medium. However, in nonlinear optics, the refractive index and therefore the speed of light in the medium depend on the light intensity. And the principle of superposition is not quite applicable. And the frequency of light, that's the color, may get altered by passing through a nonlinear medium. And photons do interact within a nonlinear optical medium so that light can be used to control it. So this is the reason why nonlinear optics is quite important and has several applications. We start with the electromagnetic wave. We know that the electromagnetic spectrum extends from the gamma rays to the radio waves, and the visible light region is a very, very small region there, from 400 nanometers to 700 nanometers. And that's where most of the C-scan experiments have been done to date. And that's where most of the optical experiments, I should say, are being done in laboratories. So we know that the propagation of the electromagnetic waves is governed by the Maxwell's equations. And let's see what's the response of the electrons in a dielectric medium to an applied electromagnetic field. So we can think of 2-3 different regimes here. In the linear regime, the induced polarization density is proportional to the applied electric field E. So we write the constitutive relation P is equal to epsilon naught chi1 E, where chi1 is the linear optical susceptibility. So in this picture, we can see an idealized atom where you have the nucleus at the center and the electrons going around. So even one electron we can take in an s orbital, for instance, the spherical orbital. And when you apply an electromagnetic field to it, we know light is electromagnetic field. And when we do that, the electrons will move in the direction of the applied field. Because this field is oscillating at an extremely high frequency, we know that the oscillation frequency of electromagnetic waves in the visible spectrum.
So dear participants, please unmute. Please mute your audio and video.
Okay, so the electrons will oscillate in sympathy with the applied electromagnetic field, and we know that the electromagnetic field has an extremely high frequency in the order of 10 to the power 14 hertz. And we can think of the nonlinear perturbative regime where the expression can be expanded in this form that we write the nonlinear polarization as the first term, which is the linear term, chi1e, plus chi2e square plus chi3e cube, where chi2 is the second order nonlinearity, nonlinear susceptibility, and chi3 is the third order nonlinear susceptibility. So we see that the induced polarization density is proportional to e square, e cube, etc. This is actually a tensor equation, but here we write it in the scalar form just for convenience. Then we also have another regime, which is the nonlinear intense field regime, where you apply a lot of intensity to the material and it doesn't exactly obey this relationship. Rather, the medium gets ionized via multi-photon tunnel and over the barrier ionization phenomena. A dense plasma is formed and free charges accelerate under the field, causing further collisional ionization. So we are not really going into that regime in this talk. So let's see what is the nature of light matter interaction in the linear regime. So from Maxwell's equations, we can write the wave equation for the electromagnetic field in a dielectric. And this is d square E by dz square minus 1 over C naught square. D square E by dt square is equal to mu naught d square P by dt square, where P is the induced polarization. So here we have used the fact that epsilon naught mu naught is equal to 1 over c naught square, where c naught is the velocity of light in vector, and E is the applied field, T is time, Z is position, P is the polarization. So for a wave equation of this kind, we know that sine waves of all frequencies are solutions to the wave equation. So it is the polarization that tells which frequencies will actually occur. So therefore, the polarization is a driving term for the solution to this equation. And now we consider low irradiances. In the case of low irradiances, we need to consider only the first term in the expansion. So we take only P is equal to epsilon naught chi1 E. And in this simple and the most common case, because almost all kind of light irradiances that we encounter in normal life, like sunlight, other incandescent light or tube light, LED light and all that, they all fall in the low irradiance regime. And so therefore, we only need to worry about the first term in the polarization. So when we put that there, the equation becomes, you can write the equation like this. On the RHS, you have 1 over C naught square chi d square E by dt square, and you simplify like this, and then the equation has the solution. EZT is proportional to E0t cos omega t minus kz. So this is a propagating wave, where omega is the frequency of the wave, which is given by Ck, where k is the propagation vector, and c is the velocity of light in the medium, which is given by c naught over n, where n is a refractive index. And we also see that n is related to the first order susceptibility chi1, 1 plus chi, the root of 1 plus chi. That is what n is. So thus, the refractive index n depends on the induced polarization, which in turn depends on the linear susceptibility chi. Now let's look at the Lorentz atom model, where you consider the atom as a classical oscillator. So we can think of the electron on a spring picture here. So in the case of the harmonic oscillator, we know the fundamental force equation is a Hooke's law, F is equal to minus kx, which can be written in the form F is equal to minus m omega naught square x, where omega naught is the angular frequency of the spring. Here you have the atom electron system as the spring. So let's take a molecule itself, the oxygen molecule. So when there is no applied field to the molecule, the centers of the positive charge and the negative charge. So this is the center of the positive charge. This is center of the negative charge. So if you don't apply any field from outside, then you can see that the oxygen molecule has no dipole moment of its own, because these two charge centers actually coincide. However, when you apply an external field, let us say we are applying an external DC field, then there will be a separation of the charge centers, and you have this creates an induced dipole with a dipole moment mu. So this induced dipole will oscillate at the applied frequency and radiate the same frequency in the normal case in the non-resonant regime. So this is what happens when you put electromagnetic radiation to matter. The dipole oscillates at the applied frequency and also emits. So we can write this, the dipole moment, as mu is equal to minus Ex, where E is the electron charge and X is the distance between the two charge centers. Now we can write the polarization density as P is equal to N multiplied by averaged mu alpha. That's the same as mu here. So this N here is the number of molecules per unit volume. And this can be written in the form P is equal to epsilon naught chi1 E. And in the more general case, as I told you earlier, this is actually a tensor equation, which means that if you apply an electric field in a certain direction, you may have a component of the dipole moment in another direction also. So that kind of a situation, you always write by this tensor expression, mu I is equal to alpha ij ej, where alpha ij is the molecular polarizability tensor. Now let's look at the nonlinear regime, the regime of the enharmonic oscillator. When the applied field is high, the restoring force on the electron is nonlinear. So you have to add these additional terms. The force now is minus m omega naught square x minus max square plus mbx cube. Like that it goes. We will see that these terms actually correspond to chi1, chi2, and chi3. So before that, we write the corresponding potential. And the potential is given by integrating f over space integral f dot dr and put a minus sign there. So this gives you half m omega 0 square x square plus 1 over 3 max cube minus 1 over 4 mb x to the power 4. So we see that there are odd terms and even terms in the potential. This is an even term in x because you have x square, which has the same value for positive values of x as well as for negative values of x. But x cubed is not like that. X cubed has a positive value for positive values of x, but a negative value for negative values of x. So therefore, if you take only the first two terms and forget about the third term for a moment, this is going to be your effective potential. So your harmonic potential is given by the dotted blue line, blue curve, but your effective potential when you add the second term is given by this red curve. So you can see that obviously this is not a symmetric potential. So the odd order terms are symmetric and even order terms are asymmetric in the potential. So what we mean is that so that's what basically happens here. Now let us consider a molecule which has a center of symmetry. The potential will be symmetric in this case. When the molecule has a center of symmetry like benzene, naturally it has the potential has to be symmetric. So the linear response is here, the nonlinear response is here. So the linear response is, of course, a parabola, as we have seen before, and that gives you chi1. But the nonlinear response here, as we have seen, the second order term is not there, and the symmetric potential departs from the parabola as you increase the value of x. So this gives you chi1 plus chi3, but not chi2. So we will look at this point once again. For a centrosymmetric potential to exist, terms containing odd orders of x should be 0. So this is the potential here. So we cannot have a term of x cube here. If it is there, the potential is not going to be symmetric. So therefore, it has to be 0. So what that means is for centrosymmetric potential, there is no driving term for chi2. Or chi2 has to be 0. So in such a system, chi3 will be the lowest order nonlinearity. We will also have chi4, chi6, chi8, etc. is equal to 0, but chi5, chi7, etc. are non-zero. But practically, these high susceptibilities, we don't really encounter them in practice. So usually, when we do nonlinear optical experiments, we can be okay with chi2 and chi3 effects. So we need anisotropic materials, that is some crystals, for generating even order nonlinear effects. Otherwise, we cannot get the second order nonlinearity. I'm trying to, okay. All right. Yeah. So let's see how these isotropic and anisotropic crystals look. What is the meaning of isotropy? What isotropy means is that, let us say I am a small, I'm very small, and I'm standing within this crystal. And if I stand somewhere here, let me look in all directions. In whichever direction I look, I see the same kind of a pattern. The reason is that there is no pattern. Okay, it is randomly oriented. So therefore, it has anisotropy. However, when we go to an ordered structure, a full crystal like this, then we see that it is perfectly ordered. And if I'm standing somewhere here, if I look in this direction, I see something open space, let us say. But if I look in this space, that's not what I'm going to see. This kind of a system is going to be and anisotropic system. So this is the reason why crystals which mostly have aligned structures like this are very good for second order nonlinearity. So here we write the potential as half m omega 0 square x square plus 1 by 3 ma x cube, and all even order, second order, sometimes fourth order, rarely. For seeing that, we need materials without a center of symmetry. Now, if you look at the order of magnitudes, for condensed matter, chi1 is of the order of unity. However, chi2 is much smaller than that, 5 into 10 to the power minus 8 ESU, and chi3 is even much smaller, 3 into 10 to the power minus 15 ESU. So these are from some very basic calculations where h is the Planck's constant, m is the mass of the electron, and E is the charge of the electron. Now let us see the generation of even and odd harmonics, how that happens, a phenomenological representation. So we are thinking about the electron system, the atom electron system, and there is the oscillation. So this is the oscillation of the incoming field, the electromagnetic field. Let's say we are giving green light or blue light or whatever, and that field is oscillating like this. And suppose the electron also oscillates in the same way like this, then what we get is something what we normally refer to as Rayleigh scattering. However, in the case of an anisotropic system, the electron is not really going to oscillate like that. The electron will oscillate a little more towards one side, but it won't oscillate that much towards the other side. So this is the result of anisotropy. Now, this kind of a behavior in time, we can actually convert that into the frequency domain by taking a Fourier transform. So if you do that, what you will see is that there is a fundamental frequency which caused the electron to oscillate like this. But in addition to that, there is also a second harmonic frequency. In other words, if you add this fundamental wave to the second harmonic wave, you are going to get this kind of a behavior. So talking in reverse, if the electron oscillates like this, then that oscillation will radiate the fundamental as well as the second harmonic. Now, in a similar way, we can think of the emission of third harmonic from a system. So here, the fundamental is again a pure sine wave. Now imagine the electron is emitting the fundamental as well as the third harmonic. So when you add these two things together, what you get is this kind of a behavior. In other words, if the electron is going to behave something like this, when you apply something like this, then the result of that oscillation is the radiation of fundamental as well as the third harmonic. It is not moving. Let me try. Yes, good. Now, there is a situation in electronics where we get distortion, what we call crossover distortion in a class B amplifier, which is very similar to the second harmonic and third harmonic generation in nonlinear optics. The only difference is that in nonlinear optics, we actually want this. So we will make systems in such a way that they emit second harmonic or third harmonic. But in the case of electronics, you don't really want this. So we will make circuits in such a way that the harmonics disappear from the system. So what we do for that is to use negative feedback. So before that, let's have a look at this is the output of an amplifier, the current amplifier stage. So a class B amplifier actually will have two transistors there arranged like this. And then the output is here, is a load, it's a speaker, for example. So the input is divided between this part and this part. The positive part flows through the upper transistor and the negative part flows through the lower transistor. However, this technique is not always very, very clean. In most of the cases, some nonlinearity will be there because the transition point will not exactly match. So if this is your input, which you have given here, let's say this is your input signal, but what you get at the output after crossover distortion will be something like this. Now look at the similarity of this with the previous picture I showed you. These two look very similar. This and this look very similar. So the result of that is that in the output, so what you hear or what you measure across the load will contain, in addition to the fundamental, higher harmonics. So this is the fundamental. It is strong, but then second order. Actually, all orders of distortion have come here because this is never as perfect as this. That's why you can see all high orders. And this produces several harmonic components which affect the fidelity of the amplifier. And we use negative feedback to linearize the amplifier and reduce total harmonic distortion. Now let us look a little closely at the second order phenomena. That's the chi2 phenomena. The nonlinear polarization here is written as epsilon naught chi2 e square. In crystal nonlinearity, this is also written in the form 2d e square. Okay. So the first thing is second harmonic generation. So we include the nonlinear terms in the polarization expression. The first term chi1 e plus chi2 e square. So this is what we are interested in, the e square term. We don't look at this term right now. Consider the second term for a monochromatic field of frequency omega given by e to the power e to the power I omega t. Now, since the electric field can be written in the form e to the power I omega t plus e star e to the power minus I omega t, which is complex conjugate. When you take the square of that, what you are going to get is this expression, e square e to the power 2I omega t plus 2 modulus e square plus e star square e to the power minus 2I omega t. So what we notice here is that there is 2 omega here. That is the second harmonic. We started with omega only because this is our original wave to start with. The frequency is clearly omega here. However, when you did this multiplication to get e square, you got second harmonic out of it. Second harmonic and something called optical rectification. This is a DC field. So second harmonic generation is just one of the many exotic effects that can arise from the nonlinearity. Now let us see how do we do this? How do we actually generate this? So the first paper of second harmonic generation appeared in PRL in 1961 by Franken et al. So here there's a ruby laser. We know that it was only in 1960 that the ruby laser was the very first laser was invented by Raman. And so that laser is used. There is a focusing lens here. Then there's a quartz crystal. And the output that comes from the whatever is transmitted by the quartz crystal is now put through a prism. And then they found that there are two beams dispersed from the prism. One is the fundamental at 6943 angstroms, that's a ruby wavelength, and the other was at 3471.5 angstrom. So it is exactly half the wavelength or double the frequency. So it was very clear that what they are seeing was the second harmonic. So this is of course, the quantum mechanical representation of second harmonic generation. We have a virtual level in between. So this is not really an absorption in that sense, because we cannot call, whenever virtual levels are involved, these are not real resonance systems, so we cannot call them as absorption. So two photons scatter in the system to produce one photon with double the energy. So that's what happens. And nowadays, second harmonic generation is very, very popular among laser manufacturers, because this is a very, very, very popular configuration. You have the 1064 nanometer output in the infrared from an Nd:YAG laser, which can be easily converted to 532 nanometer in the green region. So KDP crystals of this kind can be used for all that. So something interesting to note here. So this is the original PRL paper in which the second harmonic was reported for the first time. But if you look carefully, you'll see that the fundamental is clearly shown, but there is nothing in the second harmonic. What happened was, those were the days when papers were published not digitally, 1961. So you really have to type it out. And this was the case even when I started my PhD. So there was no Windows, no Word, nothing. So you type it out in an electronic typewriter or something like that, and sometimes write down the equations because it's very difficult to put them digitally, and then send everything by post to the journal office. So what they do there, they retype, and once they accept the paper, they retype the whole thing, and then they might do some makeover on the figures that you sent. So that is what unfortunately happened here. The person at the press who was looking at the quality of the figures, he found a small spot here. He thought it is a mistake because it was very small. See, we should remember that in this first experiment, they didn't even have the idea of phase matching and all that. So just a beam came, it was very weak, that they showed here. But the person in the press took some whitener and clearly wiped it out. So when the paper got published, there is nothing here where they claimed that the second harmonic is there. So this became an interesting aspect of this paper later on. Anyway, we know that it's really there, even though somebody in the press did otherwise. Okay, so now we come to phase matching requirements. It is not enough that we just keep the crystal there and be happy that I'll get the second harmonic out of it. So this is the nonlinear optical medium, Chi2 medium. You have the fundamental coming in omega. Let us say 1064 nanometers. So 2 omega 532 nanometers is here, and the fundamental a little bit come out. The problem here is all media are dispersive. So the fundamental and harmonic wavelengths have different propagation speeds in them because they have different refractive indices. In such a situation, the harmonic signal generated at different points in the crystal will interfere destructively with each other, reducing the conversion efficiency. Basically, the two beams, the fundamental beam is passing, it is generating second harmonic. Unless these two beams travel at the same speed, there cannot be a proper energy exchange from the fundamental to the second harmonic. So when the speeds are different, there will be a destructive interference. So I'll show that in the next slide, and you won't get efficient second harmonic. So the way out here is to phase match the fundamental and harmonic wavelengths. What we mean by phase matching is that we make the speeds of the fundamental and the harmonic equal. So how do we do that? So this is that picture. So you have the fundamental beam coming in, and this fundamental is generating second harmonic all through. So let us say it started generating second harmonic from this point. It is generating like that. And then it generates everywhere. So here it is generating, here it is generating, here it is generating. Unless the speeds are equal, these different second harmonic beams, they will not interfere constructively. They will just get added up, and they can die out actually. In extreme case, you won't get anything out of it. If you get something out of it, then that won't be very efficient. So this is the reason why we have to phase match. We have to ensure that the speeds are the same. So this is what we do. We have two conditions. One is the frequency matching condition. So that is very simple. Omega plus omega is 2 omega, which is automatically matched here. In most cases. The second case is the phase matching condition, where we write the propagation vectors k omega plus k omega is equal to k2 omega. So what it means is like k1, k2. So if this is k1 and if this is k2, then k3 has to go in the vectorial resultant direction. So in vector form, we draw like this. K1 goes like this, K2 goes like this. So this is equivalent to K3 going like this. So when you say omega plus omega is 2 omega, That is satisfied here. Now, since the magnitude of k is given by n omega by c, we can rewrite this expression in the form n omega into omega plus n omega into omega is n2 omega into 2 omega. Or in other words, 2n omega omega is equal to 2n 2 omega omega. So this gives n omega is equal to n2 omega as the phase matching condition. Or in other words, you should have a medium in which the refractive index of the fundamental beam is the same as the refractive index of the second harmonic beam. In the normal case, this is actually impossible to achieve. However, to our rescue, we have crystal birefringence, which helps us to achieve this condition. Okay. So let's see how do we achieve phase matching using crystal birefringence. Anisotropic crystals are usually birefringent. So birefringence is also known as double refraction. These materials have different refractive indices for different planes of polarization. So that is what we are going to use. So if you look here, you can see that this is a birefringent crystal, and the light rays coming from the word optics down there, which is written on a piece of paper. There are two rays coming because there are two refractive indices. And that's the reason why we can see two images here. So this is what we call birefringence. So there are ordinary and extraordinary refractive indices, which can be different by up to 0.1 for SHG crystals. And this is actually sufficient for achieving phase matching. So let's see. In this picture, we see that for the ordinary ray, this is the way the refractive index varies. And for the extraordinary ray, this is the way the refractive index varies. In fact, at this point, we have for 2 omega and omega, there's a point where we can have the same refractive index. Therefore, what we should do is to use the extraordinary polarization for omega and the ordinary polarization for 2 omega. Once we do that, we can achieve this. And NE depends on that's the important part. The extraordinary refractive index depends on the angle the beam makes with the optic axis of the crystal. But the ordinary refractive index does not have any such dependence. So therefore, if we can tune the angle for a given omega, we can tune the angle for a given omega. For some crystals, NE is less than NO, so the opposite polarizations will work. Now, this is called the index ellipsoid. So in the index ellipsoid, we can see that in whichever direction the ordinary ray has a constant refractive index, but for the extraordinary ray, it's an ellipse, and depending on the angle, you can see that the values keep changing. Now, in the case of BBO, this is the refractive index for BBO. For the ordinary ray, the refractive index varies from 1.7 and it goes down to something like 1.65 over this wavelength range. And for the extraordinary ray, if you send the beam at 90 degrees with respect to the optic axis, the refractive index varies like this. But if you reduce that to about 25 degrees, the refractive index has actually gone up. So you can raise it a little further by adjusting the angle again so that you can make it similar to NO. So this is the whole idea of phase matching using crystal birefringence. So the efficiency of second harmonic generation, therefore, certainly depends on how well you can match. So any phase mismatch is actually going to reduce or kill your second harmonic efficiency. So this is the equation for this. So you can see that, this is the output. L is the length of the crystal. A2 is the output amplitude of the second harmonic. Omega is the fundamental frequency. N2 is your nonlinear refractive index coefficient. C is the velocity of light. Chi2 is, of course, the second order susceptibility. A1 is your input. L is the length. and then you have sink square function. So sink square delta KL by 2. So if you plot delta KL by 2 on the x-axis and this, the sink square function on the y-axis, you see that when delta K is very close to 0, or when it is exactly 0, you have maximum output for the second harmonic. So this is what we have to achieve when we do second harmonic generation in a crystal. So that function, if you plot, you can see that along the propagation distance for different values of delta K, if you have delta K exactly equal to 0, then along the distance, this 2 omega intensity keeps increasing. Of course, it doesn't go indefinitely like that. It will saturate at some point like this. It is not shown in this, it will saturate like that. However, when you have delta K values which are non-zero, you are not going to get that kind of efficiency. And if the values are far away from 0, then in fact the intensities will oscillate. So that is what you see here. This is the second harmonic crystal. The fundamental beam is coming in, and for large values of delta K, intensity increases, decreases, increases, decreases, like that it goes. But when it is smaller, you have only one node here, as you can see, and when it is 0, you will not see this thing at all. So here in this picture, you can see both waves are phase matched and both waves move at the same speed. I hope it is somewhat clear from this picture. They move at the same speed, and this is the fundamental omega. The fundamental amplitude is slowly decreasing like this, and at the same time, the second harmonic amplitude is increasing like that. Now, on the other hand, if it is not phase matched, as we see here, the wave is passing through, the fundamental intensity decreases a little bit here, and correspondingly, the second harmonic increases a little bit. But however, it falls out of phase, and finally, the second harmonic output is very weak. You practically don't get much. So this is the reason why you have to really take care of the phase matching for the case of second harmonic or any harmonic generation. Now we will look at the electro-optic effect, which is actually the basis of the functioning of a Pockels cell. So we know that Pockels cells are very good for Q switching in pulse lasers. So let's see how this happens. Consider an electric field that comprises of an optical frequency omega together with a steady component, steady DC voltage. So that's what you see here. Now, this is a crystal. You apply a steady DC voltage, like let's say 2000 volts or 3000 volts or something like that. And then the laser beam is actually passing through like this. So now you have two fields. One field is the E omega field, that is the laser field. And the other field is the E0 field. E0 field is nothing but the DC field. And when you take this quantity and take the E square, so that's what we do whenever you want to do the second order nonlinear optics, then you find that there are three nonlinear contributions to this. One, nonlinear polarization is at DC frequency at 0, doesn't really affect us much. The second one is at the same frequency omega, at the same frequency omega. That is given by 4D E0 E omega. And the final one is at the frequency 2 omega, D E square omega. So if the optical field is substantially smaller compared to the electrical field, then PNL 2 omega is negligible compared to PNL 0 and PNL omega. So we can ignore this because this is the case in most situations. So therefore, we see that PNL omega is proportional to E omega. So that is what we see here. This is directly proportional to E omega, which can be written in the form P nonlinear omega is equal to epsilon naught delta chi E omega, where this quantity delta chi represents an increase in susceptibility. So that is given by 4D epsilon 0. So sorry, 4D by epsilon 0 into E naught, where this is the DC field. That's why we write omega 0 here. Represents an increase in susceptibility proportional to E naught. Since N2 is 1 plus chi, we get 2N delta N is delta chi, giving delta N is equal to 2D by N omega naught multiplied by E naught. So therefore, the medium is then effectively linear with a refractive index n plus delta n. So we start with the refractive index n for the medium, but now the medium has a refractive index of n plus delta n, which is linearly controlled by the electric field E naught. So in other words, as you apply larger and larger voltages to this crystal, the refractive index of your crystal is going to change. And that changes because of the second order nonlinear optical effect. Now let's see where we use this. Where we use this a lot is in generating nanosecond laser pulses, because most of us actually do nonlinear optics using nanosecond pulses. So Q switching is required for making nanosecond pulses. So in this example of a flash lamp pumped Nd:YAG laser, you have the laser cavity here. This mirror is not shown. Now the beam is coming like this, and you have a polarizer here. So your beam has, let's say, vertical polarization, and then it passes through the focal cell. So when a voltage is applied to the focal cell, so that it becomes birefringent. So this voltage is applied at the right time, because timing also is very important in pulse lasers. And when it is applied, the linearly polarized beam becomes circularly polarized as it travels in one direction. And when it comes back, it becomes linearly polarized again, but now the orientation has changed. If this one was in the plane of the paper, now this is perpendicular to the paper. So this beam will not be passed by the polarizer. It will be blocked. So as long as you keep a voltage on the focal cell, lasing is not possible in your laser. So this is what we mean by Q switching. The gain of the system is switched. Whenever there is voltage on the focal cell, the gain of the system is very low, because you are not allowing the laser to laze. But there is population inversion. So this is why timing is very important. The flash lamp is pumping, population is getting inverted, but you are not allowing lasing. Then suddenly, after a few nanoseconds, you will allow lasing to happen. So if you do that, then you will get all the energy that was in the cavity. So the cavity was building up energy. So all that energy will come down in stimulated emission as a very, very strong pulse. And that is the Q switched pulse, which is much more powerful than the non-Q switched pulse. So this is the idea of the focal cell. Now let us look at three-wave mixing phenomena. That is also very important in all second order phenomena are basically, including second harmonic generation, are basically three-wave mixing phenomena. So we will look at this in a little general way now. Second harmonic generation was just an example of this. So when two optical waves of frequencies omega-1 and omega-2 travel through a Chi2 medium, they mix and produce a polarization density with components at a number of frequencies. So let's assume that some frequency generation omega-3, omega-1 plus omega-2 satisfies the phase matching condition. And once omega-3 is generated, it can interact with omega-1 to generate a wave at omega-2. And similarly, omega-3 can interact with omega-2 to generate omega-1 is equal to omega-3 minus omega-2. So therefore, the three waves undergo mutual coupling in which each pair of waves interacts and contributes to a third wave. This is what we call three-wave mixing. Now, this is the full expression for this. You write ET with two fields with frequencies omega-1 as well as omega-2. And when you take ET square for this, you have a long expression. And this expression contains second harmonic generation at 2 omega-1, again second harmonic at 2 omega-2, some frequency at omega-1 plus omega-2, difference frequency at omega-1 minus omega-2, and DC rectification at omega is equal to 0. Doesn't mean that all these waves, all these phenomena will happen at the same time in the crystal. That won't happen because there are phase matching constraints. So essentially, there is some generation, there is difference generation, there is spontaneous parametric down conversion. So which phenomenon happens is also dependent on what is the input you give. When you have two small frequencies as the input, you have some frequency generation. When you have two high frequencies, you have difference frequency. And when you have just one high frequency as the input and two small frequencies the output, you have spontaneous parametric down conversion. Now, SPDC is quite important because of a number of reasons. So this is the diagram for this. You have the pump, and there is a signal, and we call the idler, signal and idler. Momentum needs to be conserved. This is a phase matching condition. K pump should be equal to Ks plus Ki, and energy is, of course, conserved. And now the importance of SPDC is that the signal and idler photons are actually entangled in polarization, position and transverse momentum, angular position and orbital angular momentum, time and energy. So that is the advantage of having SPDC in a system. And this kind of entanglement is important for fundamental tests of quantum mechanics, that is non-locality, and in quantum technologies, for example, in secure communications. Nowadays, everybody knows about the arrival of the quantum technologies for making very secure communications, which people cannot eavesdrop. And a lot of work is happening in this direction. And my colleagues, Professors Urvashi Sinha and Andal Narayanan at RRI, they actually work in quantum optics, entangled photons and related applications. So this is a diagram of optical parametric generation. It's the same as SPDC. So you generate signal and idler. When you put it in a cavity like this with mirrors, that becomes an optical parametric oscillator. And you can also make an optical parametric amplifier by taking the energy of one wave and giving it to another wave. For example, in this diagram, there are two inputs. So the energy of omega-3 is taken by omega-1, and in the process, omega-2 is formed. Omega-2 is omega-3 minus omega-1. So these are generally known as optical parametric amplifiers. And now we will look at the third order phenomena, where the nonlinear polarization is characterized by epsilon naught chi3 e cube. So here we have interesting phenomena like optical Kerr effect, nonlinear refraction, two photon absorption, third harmonic generation, etc. And the third order susceptibility here, because I mean, this we see in a system where is no second order nonlinearity, because if second order nonlinearity is there, that is much, much stronger than third order nonlinearity. So these are systems which are isotropic, and you don't have the second order term in the potential, only the third order term, so which is even. And so you get this kind of symmetric potential. And if you
yeah, 5 minutes.
5 minutes. Okay, yeah. Okay, I'll finish in 5 minutes. So third harmonic generation, nonlinear refraction, nonlinear absorption. So these are some of the outcomes of the third order nonlinearity. So third harmonic generation here, H cross omega becomes 3 times H cross omega. We have the expression here. And in optical Kerr effect, what happens is the refractive index changes as a function of the intensity. So the expression for this is n is equal to n0 plus n2i. This is the way you actually calculate it, not going into the details because of time constraints. So there are different materials with good values of n2, like chalcoidinides, tellurides, silicates, borates, phosphates, fluorides. People often do a lot of studies on these. And self-phase modulation. So this happens, this is something what we call self-focusing. If you have a Gaussian beam and that goes through a third order nonlinear medium, then it is quite possible that the beam will focus like this. So this is known as self-focusing, and this is actually used in Kerr-Lenz mod locking for generating ultra-fast laser pulses. For example, our ultra-fast laser is a Kerr-Lenz mod locked ultra-fast laser. So where the when the pulse is passing through, there is self-focusing. So you put an aperture here so that when the pulse is not formed in the cavity, it's a bigger beam and it does not really has efficient passing through. So only the mod lock pulse will pass through. This is called Kerr-Lenz mod locking. And so this is a train of ultra-fast laser pulses seen on a 100 MHz oscilloscope in our lab. So at the rep rate of 82 megahertz, the pulses are separated in time by only 13 nanoseconds. Just note that no oscilloscope works as fast as 100 femtoseconds. What you see is a much elongated pulse here, but the distance between them is 13 nanoseconds. So therefore, you are able to see this even on a small oscilloscope of 100 megahertz. Now, I will talk about pulse spectral broadening by self-phase modulation, and probably I think I'll be finishing by that. So if you consider a light pulse propagating free space in this form, you write E is equal to E naught e to the power I phi, where phi is the phase, which can be written as omega 0 t minus kx, where k is given by omega 0 c by n. The instantaneous frequency omega t is the time derivative of the phase, as we know, and that is given by omega t is equal to d by dt phi t. In the normal case, for this quantity, what you get here is omega naught, because n is a constant for free space. Now, this is for all good for linear things. However, when you come to a nonlinear medium, a third order nonlinear medium, the refractive index itself is given by a naught plus n2 it. And for a Gaussian pulse, if you consider, the intensity varies in time like this. Now, when you make all these substitutions into your previous equation, you see that the instantaneous frequency is not a constant. In fact, in addition to omega naught, there's an extra term here, and that extra term becomes important if di by dt, that is the rate of change of the intensity. If this quantity is large, then you are going to have a large value here. And of course, this is large for an ultra-fast pulse. So therefore, it is very clear that when you send an ultra-fast laser pulse through a third order medium, it is quite possible that the instantaneous frequency is going to change. So this is what happens. So we have time here, and this is the intensity of the laser pulse, and then the instantaneous frequency is going to change like this. So initially the instantaneous frequency goes below omega naught, the central frequency, but then it goes above omega naught. This is what we called chirping of the laser pulse. So the self-phase modulation expands your pulse in the spectral domain. So you started off with a pulse of this kind with the same central frequency here. However, the positive part becomes red shifted and the negative part becomes blue shifted because of chirping, because of this equation. And what you get outside here is something that has much more spectral bandwidth than what you started off with. So the extreme case of this is supercontinuum generation. So here, this is done in our lab, actually. We are sending the femtosecond laser pulses, amplified femtosecond pulses, through water, just water. Water is a good nonlinear medium for if you are using highly intense laser pulses, and see how much it has. It actually gives you a rainbow like this. So water is good. CAF2 is much better. Photonic crystal holy fibers are very good. So in addition to SPM, we also have stimulated Raman processes for mixing, etc., which contribute to supercontinuum generation. Then we can also have solitons. In the case of temporal solitons, the chirping, which I told you just now, can be compensated by something called group velocity dispersion. I cannot go into that, what exactly it is right now, but it's a linear phenomenon. This linear phenomenon compensates for this nonlinear phenomenon. And then you get a soliton, which is a wave that propagates without changing its shape or temporal width. So you can have solitons in time, you can have solitons in space also. For example, the diffraction of a beam can be compensated by self-focusing. And when they exactly compensate, you can have a spatial soliton that travels without changing its shape. This is particularly useful in optical fibers. Okay, so I am not really going into, because this part will be spoken in much detail, I'm sure, by Professor Venugopal Rao and also by Vinita, I believe. So just to say that nonlinear absorption has 2-photon absorption in that. And we can also have, if you take organic molecules and all that, then polymers and all that, then we can also have, let me go to, also have 2-photon absorption there. And as well as, in addition to that, we can have 2-photon fluorescence there. And four-way mixing is there. That is another aspect of third order nonlinearity. And just 1 minute, effective third order nonlinearity is cascaded processes Chi1 is to Chi1. Professor Sheikh Bahai mentioned Chi2 is to Chi2 processes, but we have Chi1 is to Chi1 processes, which are essentially saturable absorption, excited state absorption, free carrier absorption, etc. And in the refraction part, we can have molecular reorientation, state population redistribution, thermal refraction, all that can happen by cascaded processes. So it is important that we actually distinguish between two photon absorption and excited state absorption, for instance, but I don't really need to discuss this too much. So this is excited state absorption where you have real levels in between. And if you are talking about two photon absorption, then this won't be a real level. It will be a virtual level actually. So now the Z-scan, that is what we are about to discuss in the other talks here. So the Z-scan is good for measuring. It's very good for measuring the nonlinear refractive index as well as the nonlinear absorption coefficient, depending on whether you use the open aperture or the closed aperture Z-scan experiment. So expertise in Z-scan is something that you gain over many, many years. And I should say that even today, I am learning interesting things in Z-scan in my lab, working with my students. And it's a fantastic experiment. You learn a lot of things from this and a lot of intricacies in that, which I'm sure will be discussed in the lectures that will follow. And I have to thank the following resources for making this lecture. Fundamentals of Photonics by Saleh and Tai, 3rd edition. Then Handbook of Nonlinear Optics by R.L. Sutherland, Nonlinear Optics by Boyd. Then there are some very good online lectures available in the net by Boyd, by Van Stryland. Then from Brown University, I could find some PPT files which are good. Then Wikipedia and then internet in general. So this talk is prepared on the basis of all these resources. And thank you very much for the kind attention. I'm sorry I had to rush a bit because time was limited. Thanks a lot.